Okay. And just provide a roadmap. Before I begin, I want everybody to get sort of a brief understanding of what it is that we're going to be talking about, and then come back to these themes throughout the talk so that we remain on target. So first, I want to convey to you what it is that the Urban Climate Research Center actually is. Who are we? What do we do? What is our vision? And how do we hope to connect with all of you and others that are not here? So we focus on 5 thematic areas for the Urban Climate Research Center, but I actually like to think of it even more broadly. As I mentioned before, I do some agricultural type work, renewable energy type work, and of course there's renewable energy integrated in urban environments, but then there's agriculture outside of urban environments. So we're even broader than the communique that I'm going to be transmitting to you over the next 20 to 30 minutes. I'm going to demonstrate. I only took out a couple of very successful, oh no, actually after that, then Joseph comes. And he's going to talk to you about some of the societally relevant work, how we're recontextualizing, how he's recontextualizing heat-related mortality and morbidity. And then I'm going to finally conclude with some examples of recent success of the UCRC, with the understanding that I really don't have the time, nor do you probably have the patience to go through a whole laundry list of every NSF or Department of Energy grant that we have gotten. So at this point, Allison, I'm going to segue to
the Urban Climate Research Center at Arizona State University delivers transformative scientific advancements and urban climate solutions for diverse communities and ecosystems around the world. We coordinate, educate, facilitate, and support municipalities in the United States and around the world, focused on developing science-based urban environmental solutions. We are social and physical scientists, planners and designers, health researchers and engineers. We focus on understanding of urban climate dynamics, urban climate modeling and projections, heat mitigation strategies and impacts, observational measurements, and human health and well-being. Find out how the UCRC at ASU can help urban climate solutions for your community. Contact us today at urbanclimate@asu.edu.
Wonderful. Thank you so much. And as I mentioned a few minutes before offline, you were the first group to actually see that video. That video was just concluded last week, actually. So hopefully it was informative and begins to at least scratch the surface of what it is that we do. So for the next few minutes, I want to just jump in a little bit more into each one of these 5 thematic areas to give you a bit of a better understanding illustration of what we do and how we do it. So the first of these themes, and they're in no particular order. Again, we are the Urban Climate Research Center. We are not a degree granting entity. We are under the School of Geographical Sciences and Urban Planning and School of Sustainability. And really our initial mission is to produce state-of-the-art science, because we can't be out there making recommendations to municipalities and cities and various stakeholders unless we can stand behind our science. And our science really consists of trying to characterize, better understand why precipitation outcomes occur, why temperature outcomes occur. So improving understanding of urban climate dynamics is really at the forefront. Again, we're in the School of Geographical Sciences and Urban Planning, but our leadership team consists of faculty from School of Mathematical and Statistical Sciences, School of Sustainability, the Design School, Engineering and the Built Environment, Arts, Media, and Engineering. You're kind of getting the picture that we are truly a diverse and interdisciplinary group. And that's really the point. Gone are the days from 20 or 30 years ago, or maybe even as recently as 10 years ago, where you would have an urban climatologist trying to promote various solutions that are going to make cities better. That's not enough, right? We know now that trying to promote improved livability and well-being in cities really requires an interdisciplinary approach. So let me start by going into each one of these themes, improving understanding of urban climate dynamics. I'm an atmospheric scientist and I'm a climate modeler in particular. And so I use climate models to get at some of these key outcomes that everybody's really interested in. Before we can understand heat health impacts, we need to know how is heat going to change in the future? How are temperatures going to change in the future? So we're interested in not just what the outcome is, but what are the specific processes, physical processes. And so in doing this, we use what are referred to as regional climate models. So they're models that represent the atmosphere using fundamental principles, mathematical principles, and we apply these models at our geographical area of interest. Could be Arizona, could be the United States, it could be the globe if you're using a global climate model, and we've used those as well. Global climate models, when you've read your favorite CNN article or any other news media, you might see a reference to these models predict or these models project. More than likely, you're reading about global climate models. And there's a reason that we use regional climate models, because they're higher resolution, provide more fidelity in terms of actual outcomes. And so we're interested in a vast array of outcomes, not just temperature. The video highlighted temperature. The UCRC is well known for doing a lot when it comes to heat mitigation, but we do the whole suite, the whole gamut of urban climate environment. So for example, somebody might have a question, and this is particularly relevant today, given the stream of tropical moisture through the Southwest. For the meteorologist out there, Scottsdale, I think, had a dew point of something like 72 or 73 degrees Fahrenheit. That's an absolute measure of moisture. That is the type of number that you get in Miami when it's moist. Okay, it's very unusual for us to get those sort of moisture values. And so we're interested in extreme temperature, extreme precipitation, and the causal mechanisms, right? This is where we differentiate ourselves from statistical processes and statistical methodologies. It's not just the outcome, but what are the driving physics that are responsible for this outcome? Part and parcel of this is our ability to conduct projections. This might include temperature projections, and what I'm showing you here on the left-hand side are summertime temperature increases for the end of the century for the continental United States that result from the growth of cities or urban expansion and greenhouse gas-induced climate change. This is important because these are two separate, what we like to refer to as forcing agents, two separate causal mechanisms. Greenhouse gases, they have an impact on climate. The urban environment has a separate, independent of greenhouse gas emissions, effect on urban climate. And so we like to conduct these projections to try to understand what is the worst case scenario. Okay, how do different models simulate these pathways of urban expansion and these pathways of greenhouse gases differently, because all models are not created equal. So we want to get a sense for the uncertainty. These models are just that, they're models. They're not crystal balls, and there's always some level of uncertainty associated with them. For illustrative purposes, on the left-hand side here, I'm showing you daytime impacts, and you can see that these are values in Kelvin, which is the same as centigrade. So if you see these dark reds, that's 4 or 5 kelvins, 4 or 5 Celsius. Let's multiply that by 2 so that we can get the answer in the equivalent answer in degrees Fahrenheit. So wherever you see these purple shadings, we're talking about 8, 9, 10 degrees Fahrenheit warmer by the end of the century compared to the start of the century. That's pretty significant. And on the right-hand side, we see the equivalent temperature projection during the nighttime hours. So during the nighttime hours, you're seeing a much worse situation. The top row was for one global climate model feeding greenhouse gas information into our regional climate model. And the bottom row is for a different global climate model feeding greenhouse gas information to our regional climate model. Again, getting into this sense of uncertainty. Like, how certain are we that we will expect that we should expect temperature warming of 7, 8, 9 degrees? And the answer is we're pretty certain. Okay. But we also focus on precipitation. So for example, here's an illustration of end of century precipitation change, mean precipitation change for the state of Arizona. If we look at the top left, according to these results, we should actually expect a slight precipitation increase for the state of Arizona. This is one out of many possible realizations. But the notion that we are assuredly going down a pathway with minimal precipitation certainly is not credible. That may be the realization, but there's other simulation output that suggests otherwise. Now, this is only part of the hydrologic cycle. Of course, P is only a part of the component. You also lose water through evaporation, and that gets to a more comprehensive analysis of the broader hydrology of the southwestern United States. But what I want to highlight here is our ability to focus on continental scales on the left, our ability to focus on state or regional scales on the right, or our ability to focus on the scales of individual neighborhoods or on the scales of individual cities. For example, we can conduct our modeling simulations all the way down to the neighborhood scale and produce the same sort of temperature or precipitation output down to the neighborhood scale, so that we can begin to prioritize adaptation solutions. For example, here we have, from a relatively recent paper, a heat sensitivity index, which is illustrated by these red shadings. And a very relevant question might be, well, what if we deploy biophysical solutions like street trees or reflective pavements over those areas as compared to other areas? What is the outcome? Okay. When speaking about heat mitigation strategies and impacts, and this was pretty big across the news this summer, you may have come across your favorite media outlet that indicated that these scientists from Georgia Tech and University of Michigan and Arizona State University, this was led by Brian Stone at Georgia Tech, concluded that a concurrence or simultaneous heat wave and blackout effect could have dire consequences for heat-related mortality and morbidity for, in particular, Phoenix. Atlanta is a concern, and Detroit was the third city that we investigated, and it was less of a concern. We're not projecting, we're not stating that this will happen, but we are indicating that the likelihood, if this were to happen, the likelihood of dire consequences would be pretty significant. We want to ask the question for the local municipalities, are they prepared? What we calculated with this work was that in such a situation where we have a concurrent heat wave and blackout effect, some 80,000 Phoenicians would require hospitalization. And then the question that we have is, okay, what if we incorporate street trees? What if we incorporate cool roofs? To what extent are these impacts going to be ameliorated? So this directly speaks to the notion of heat mitigation strategies and impacts at the city scale. We also conduct observational measurements, and this is particularly important because from a modeling perspective, we need observations to convince ourselves and our readership that the model is behaving appropriately, that it's reproducing the appropriate meteorology, that it's reproducing the appropriate air quality, temperature, wind speed, wind direction. And we have observational measurements at multiple scales. One of these scales is down to all the way on the right-hand side labeled Marty. This is courtesy of Ariane Midel and her Shade Lab, all the way down to the pedestrian level. This is really unique because it gives us an indication of thermal properties that we don't normally consider. What could this be? Well, I often say 110 degrees, assuming that it's dry, isn't all that bad. And before you all think that I'm crazy, let me take another step forward and explain myself further. People actually pay a lot of money to experience temperatures that are a lot warmer than that. They're called saunas. So what makes it so difficult in 110-degree weather or warmer in Phoenix? What makes it so unbearable is the moment that you step outside into the direct sunlight and you feel 1,000 watts per meter squared, or whatever the value might be under cloudless conditions. That combined, that radiation load combined with these extreme temperatures has the likelihood to make things really, really dangerous, especially for those that are most vulnerable, the elderly and newborns. And of course, others with comorbidities and other health-related impacts. So MARDI that you see here on the right-hand side offers us an opportunity to get a sense for how this MRT, mean radiant temperature, this new metric, it's not new, it's actually been around for a long time, but it's difficult to communicate, for how this metric varies across our landscape. And it really allows us to quantify the importance of providing shade, any kind of shade. It could be natural shade or it could be engineered shade. For example, shade due to a photovoltaic platform that is simultaneously making things more comfortable during the day while also providing electricity generation. That's really important. Okay. In addition to some of these platforms, we also do non-urban observational measurements. For example, what I'm showing you here is what is called an eddy covariance tower. The tower measures wind speed very, very rapidly, every, let's say, 15 or 30 seconds. And it allows us to get really important information related to how turbulent the lower atmosphere is. So it gives us much more than just radiant temperature. It gives us much more information about properties that are necessary for understanding the characteristics of the lower atmosphere. And we conducted these measurements and have the capacity to do this in other locations, and we'll do so, at a solar PV site. This is managed by APS and ASU jointly, about halfway between ASU, Tempe, and Tucson, maybe 2/3 of the way, and a reference location. And this was important because it allows us to develop an electricity, a PV module, a photovoltaic module, that we then connect to our regional climate model. The one that I showed you before is allowing us to make all these simulations about temperature and precipitation, and also the physics that leads to those outcomes. And it allows us then to provide all of that information in addition to electricity production. That's really important because we live in the aptly named Valley of the Sun, and we need to get objective numbers on the capacity of electricity production in our deserts, over our urban neighborhoods. But these models, these physically based models, again, must be grounded on observed conditions, observed quantities, because anybody can run a model. The question is your model realistic? Is it producing appropriate meteorology, climate, electricity production, so on and so forth? So we've developed this model, and we're actually moving forward with these specific calculations right now to answer this specific question. If we deploy over the desert, so these are non-urban landscapes, over the desert locations, what is the impact on meteorology, and how much electricity can we produce? We can ask very similar questions of urban environments. This is very important, right? Because it's much easier to communicate to somebody such that it makes a direct connection and it has meaning for them. Well, if you install a PV over your house, you're going to save 50 or 75% or more off of your electricity bill in June, July, and August, rather than it will be 1 to 3 or 4 degrees Celsius, Fahrenheit or centigrade, whatever unit you want to use, warmer. That has less impact on an individual. So from a human health and well-being, I go back to the illustration that I showed you a few minutes ago about the heat sensitivity index, spatially variable heat sensitivity index for the metropolitan area. And what we said was, okay, using our numerical model that we've evaluated, we've compared it to meteorology, and it does very well against temperature and solar radiation and so on and so forth. And we said, well, what if we deploy cool roofs over those pockets of the Phoenix metro area that are most sensitive to heat? Okay. And what you see here on the right-hand side, this is a full, what we call a diurnal cycle. So it's a full 24-hour period. It's actually an average over, I believe, 1 or 2 weeks, but we averaged it into a full 24-hour period. And what you see here is that if we deploy reflective roofs over those most heat-sensitive areas only, that's 10B, then you get a thermal profile. Like if you can follow my cursor, it's this darker, Joseph, what color is this? It's like a darker red, I guess. I'm a little bit colorblind here, so you'll excuse me. Okay, so you achieve cooling of about a 0.5 degree Celsius. Okay, and then the question is, so that's a small fraction of the metropolitan area. Then the question is, what if we deploy those reflective roofs everywhere? That's cool all. Well, if you follow that purple line, you achieve additional cooling of about another 1/4 degree Celsius. This has really important economic implications and practical implications, such as, what is the required labor associated with placing these cool roofs everywhere? And what is the additional cooling that we would get? So this is an extra added component of the modeling capability that we get, is we can conduct what-if scenarios at continental scales, at the scale of an individual state, and I've done work over California, over other countries as well, or even drilling down into the metropolitan area, all the way down to the individual neighborhood. Okay, now I'm going to pass the baton to Joseph, who's going to talk about an issue that is particularly important, really not just for Phoenix Metro, but I would argue for all major cities in the United States. So I'm going to pass the baton to you.
Thank you so much, Professor Georgescu. So I'm Joseph, and I'm mostly going to build up on what Professor Georgescu has been presenting on. Specifically, my slides are going to focus on 3 research focuses for the UCRC, one of them being heat mitigation and impacts. And then we have observational measurements, and then human well-being and health. So in my first slide here, the biggest question that we're asking is, how does the geographical context, physical and social economic processes systematically contribute to heat-related outcomes in Phoenix? In this context, the geographical context refers to the intrinsic locational characteristics that define the vulnerability of a population or a location. So that's what the geographical context means in this slide. And so what role can science play? And we know that science can play a significant role or a central role in terms of the responses, that the responses that we derive or the responses that we formulate should be targeted towards certain populations or to certain locations. Secondly, is that the targeted intervention should also be commensurate to the nature, magnitude, and scope of the hazard at hand. And that's why, as scientists or at the UCRC, we are trying to understand these bigger or larger questions that define vulnerability, both in terms of the physical and the social economic context. And then just building up on that, the diagram here illustrates some of the areas or aspects of science where there lies opportunities for incremental improvements when it comes to understanding vulnerability science. And one of the things here is that we've got to re-examine the data choices that we have. And the examples of the studies that we have in the subsequent slide will demonstrate that. And then how does our understanding of statistical associations and theoretical relationship between variables vary? What disparities exist and what opportunities exist for harmonizing these two things so that we can have improvement in how we conceptualize vulnerability? Then we've got modeling and statistical transformations and the implications that they have in terms of identifying vulnerable groups or vulnerable populations. And when you think about it, is when we are developing, for instance, a sensitivity metric, as Professor Josicki has been explaining, how do all these components of vulnerability influence decision pathways? And how does it inform science, which could in turn help in safeguarding lives and as well as reducing heat-related morbidity or mortality? And also in this context, how does geographic information science aspects? We know GIS has been mostly used as the platform or the infrastructure for visualization of vulnerable groups and vulnerable locations. So how do the aspects of geographic information science, how can we leverage on them so that we can have targeted interventions? So one of the studies that we conducted was done for the city of Phoenix, where we used 911 as one of our outcome variables. And one of the key findings was that homelessness was the single most important variable for predicting heat-related outcomes. These are very significant findings because homelessness is not one of the variables that are found within the census dataset or socioeconomic datasets that we use mostly for mapping vulnerability or for developing vulnerability indices. The other key finding here is that the choice of input variables as well as model type influence the understanding of heat health outcomes. So when you look at these two significant outcomes of this study, I want you to think in terms of the larger context, what it means for developing of vulnerability metrics. What will that mean in terms of the local stakeholders, like for instance, the city of Phoenix, when it comes to them developing vulnerability or rather strategic resilience and then response outcomes with regards to the city of Phoenix and the certain pockets of locations or populations. So the key variable here is homelessness. And besides that, we also have populations walking, percentage of vacant houses. And then we also are able to quantify the geographical context. And remember, these are the intrinsic characteristics of a population or a location that predispose people to vulnerability. So the larger context here is that we've got neighborhoods that have got specific nuances when it comes to vulnerability, and that the influences of these variables are not uniform. Each neighborhood has got its own unique characteristics that have got to be brought up through breakthrough science, or rather science that picks up the most vulnerable locations and the populations. And then the second study demonstrates one of the intervention strategies that is used by the city of Phoenix and also the Human Services Campus, where we provide tents to mostly the homeless population as a means of improving or rather improving their privacy, and then secondly, to protect them against direct sun exposure during the sweltering summer months. And what we found out from this study is that using tents or tent covers may not protect from the extreme heat for the unsheltered homeless. If you go to the streets in Phoenix during the summer, you'll see tents which have got additional cover materials. But what we are finding out is that adding the additional cover materials on top of these tents does not safeguard against heat vulnerability. In fact, most of the tent cover materials, as you can see from all these diagrams, is that they tend to increase heat vulnerability. What I have here is that this shows heat during different times of the day. For instance, this is for during the daytime, and then this one shows for nighttime, and then diagram C shows like the combined day and night characteristics. And the key takeaway is that different tent cover materials are not an effective means of protecting or safeguarding the homeless community from the intense heat, especially during the summer. And so these findings are really crucial for rescue missions, local governments, and public health officials and the general public, that maybe we should reconsider or re-examine some of the interventions when it comes to protecting the most vulnerable. Thanks for listening to me.
Thank you very much, Joseph. And of course, we'll be happy to take questions on all of this and even related questions when we conclude in a few minutes. But I just want to highlight one of the reasons that I asked Joseph. Well, one of them, he's a prolific speaker and just an absolutely incredible student. But the other is to just highlight
once again, I have my PhD in atmospheric science. I have traditionally worked with engineering and natural scientists. That's not what the UCRC is. Okay, now I want to hammer that home. At the Urban Climate Research Center, we are combining in unique ways that other entities across the world are not doing. We're combining social sciences and social approaches with natural sciences and engineering approaches to try to figure out what we can do. First of all, what is the specific problem? And then what can we do by working with cities and municipalities and stakeholders to improve conditions. I only want to highlight a couple of recent success stories. There are many more. Apologies if you've worked with the UCRC in the past and don't see this listed. I take it upon myself as having made that mistake. One of these is a report that was produced by the UCRC for the city of Scottsdale, which focused on, first of all, identifying the locations of greatest heat using remote sensing and land surface temperature type of analysis, and then producing a range of plausible pathways that would lead. Appreciate, Lisa, thank you for the waving. I did see that out of the corner of my eye. Highlighting pathways to reduce the burden of heat. Okay, so these sort of communications are really important. There are ways that we can go even towards the next step, and I'm happy to discuss this as well. Even more recently, this is a project that started, I believe, summer of 2020. So during the summer where COVID was in full swing, where the city of Phoenix, and in particular the Department of Transportation, started laying down a particular type of coating on road surfaces to increase the reflectivity of the road surface and therefore decrease the amount of absorbed solar radiation. And I'm happy to report that as of this summer, sometime in the middle of July, the Cool Pavement program of Phoenix eclipsed 100 miles of cool coating across the Phoenix streets. So what does the UCRC do in this case? Lots of measurements. We go out there, not myself, but others, we go out there and measure the before, measure the after. There's helicopter voyages to get more comprehensive forest from the trees type of look of these are the locations that have this cool sealant and how do they compare at the same time with locations that don't have this cool sealant. We've worked in consulting. This is one example through the ERA Association. That's basically a manufacturer of roofing products. I've worked with ICF, which is a global advisory and technology service. We've worked with utility companies in Arizona. With 3M, they produce a cool sealant. The number of collaborations are increasing, and that's really our mission, is to try to use our best approach at conducting the science, which we know is at the forefront of what is expected, and to try to connect with those on the ground so that we can not just produce papers, but we can make a difference. So with that said, I'm going to stop here. That'll conclude the formal portion of the presentation, and Joseph and I are happy to take on questions and hopefully formulate a lively discussion. Thank you.